So today this is the eigen function of the LTI system. So that is the topic that we are going through now. So for the LTI system, we know that the output is given as the convolution of the impulse response and the input, and this is for the continuous time system. Okay, and this is for the discrete time system. So let's say input is let's say z to the power n. Okay, so when you apply this as an input to the system, what will be the output? So you just replace this input with here. So you'll get z to the power n minus k and h of k and this summation sign. Okay. Now, since this summation is over k, you can take the z to the power n outside because this is independent of k, and then you will be left with this number. Okay. Now, if you see this term here, this is independent of n, or I can say independent of time. This is dependent on something called k, and once you sum it over k, the k will go away, and then you will be left with z here only. So you can say this complete thing is a function of z. So it is not function of time, it is function of z, and that's what we call it as a h of z. And later on we will see that this h of z is actually the z transform of the h of k. Okay, so if you see this output y of n, this is same as input multiplied by h of z, which is independent of time. It is some you can think of this as some kind of constant which is independent of time. Okay, so output is input multiplied by some constant. Okay, so whenever you have an input which gives the output such a way that output is input multiplied by some constant which is independent of time, those kind of function we call it as a eigen function. Okay, so any input which gives the output same as input multiplied by some constant, so those input we call it as a eigen function. Okay, so this z to the power n, you can say that it is a eigen function of discrete time system. Okay, discrete time system. Okay, and this h of z we call it as a eigen value. Okay, so this z to the power n is a eigen function and h of z is a eigen value. Similarly, for the continuous time system, if you, let's say you have input e to the power st, and when you apply this input this into this equation, you will replace this input with this e to the power st, so you will get this term here. Okay, you are just replacing this xt minus tau with e to the power st minus tau. Again, since this integration is with respect to tau, the e to the power st you can take it out, and then this will be the integration. Okay, and this integration, if you see, this is again independent of time t, and it is a function of s. Okay, so this is function of s, and this we call it as h of s, and that is what we call it as a Laplace transform of h of tau, or you can say h of t also if it is a function of time. So in this case also, output is same as input, which is e to the power st, multiplied by some constant which is independent of time. Okay, so here hs we call it as an eigen value, or you can say it is a Laplace transform also, but here in this slide we will call it as an eigen value, and this e to the power st we call it as eigen function of this continuous time LTI system. Okay, so in the LTI system, whenever input is in the form of z to the power n for the discrete time, or e to the power st for the continuous time system, your output will be same as input multiplied by some constant. Okay, so this is the property of the eigen function. Okay, so any input which you give to the system and output is like input multiplied by some constant, then those kind of input we call it as eigen function. Anyone has any doubt here?
No doubt, sir.
Let me go to the next slide. So in one of the IES paper, this problem was asked. So a response to a system to a complex input is given as this. Okay, and the output is specified as this. So this is the input, and for corresponding this input we are getting this output. Now we need to find out whether the system is LTI or not. Okay. So just now we saw one example that whenever your input is e to the power st, your output will be something like e to the power st multiplied by some h of s, okay, which is independent of time t. Okay. Now if you see this e to the power st and if you see this e to the power j to t, both of them are kind of similar. Only the thing is that you can just replace this s with 2j. Okay. So when you are applying an input as e to the power 2j t, wait. So when you are applying this as an input, what will be the output? So output will be same as input multiplied by some constant. But in this, so this is the case when you have the LTI system. Okay. If you have LTI system, if this is the input, then output should definitely be in the form of this. Okay. But if you see this, this output is not in the form of this, right? Here you are getting e to the power j 2t multiplied by something which is not independent of time. It is depending on time. And other than this, you are getting some extra term here. Okay. And this term should not have come at all. Okay. Because in at input, when you are giving e to the power j 2t, at the output also you should get e to the power j 2t only when it is a LTI system. Okay. So based on this eigenvalue concept, you can conclude that the system that is specified in this problem is not a LTI system. So this is the this B option is the correct one. Okay. Anyone has any doubt in this problem?
Maybe.
And let me continue then. Now, just now we saw what is the Laplace transform. So I will just elaborate more here. So here the Laplace transform is given by this formula, that is and we also call it as a bidirectional because here the limit is from minus infinity to infinity. Later on we will see that this limit can be from 0 to infinity for the unidirectional. That is something different concept at all. Okay. Here we will see only the bidirectional. So in this case, this s that you see here, this is a complex number, and we here sigma is the real part and the omega is its imaginary part. Okay. So for any signal or any time domain signal x of t, the Laplace transform will be given by this formula. Okay. So once you do the Laplace transform of time domain signal, the resultant signal, which is x of s, will be function of s. Okay. Which is a complex variable. So generally, when this is how we represent the Laplace pair xt, and then there will be like arrow kind of thing, and then x of s. So this represented that these two are the Laplace pair. So this is how we this is the formula that we are going to use to calculate the Laplace transform. Now let me go to the next slide. Now let me take an example that let's say we have a signal xt is equal to e to the power minus at ut, and for this particular signal we want to find out what is the Laplace transform. Okay. So let's put this x of t into the Laplace formula. So we will get e to the power minus at ut e to the power minus st. Okay. Since here we have a ut term, instead of doing the integration from minus infinity to infinity, we will do it from 0 to infinity and just remove the ut. So resultant will be like this. Now this can also be written at like this. I've just taken the e to the power minus a plus st common. Okay. So when you do this integration, you'll get this, and you have to put the limit 0 to infinity. Okay. Now when you put the limit equal to 0, this e to the power term will become 1. But when you put infinity here, okay, so this is how it is going to look like. Okay, when you put put the infinity here. Now this Laplace transform, the second term of this Laplace transform, here you see, can become infinity or it can become 0 depending upon the value of this a plus s. Okay. So now let me put s equal to sigma plus j omega, where sigma is the real part and the omega is the imaginary part. So once you put this, this is how it is going to look like. Okay. Now in this complete expression, we have this term e to the power minus j a plus alpha into infinity. Now this complete term that you see here, this, it can either be infinity or it can be 0. Okay, so what is the condition that it can be infinity? So infinity is the condition when this e to power something is a positive number. So when it is a positive number multiplied by infinity will become infinity, and when it is a negative number it will become e to power minus infinity, and hence it will become 0. Okay, so here comes something called the convergence of the Laplace transform. So we want this Laplace transform to converge to some finite value. We don't want it to go to infinity. Okay, and because of that there is some condition on this a plus sigma, and that condition is that a plus sigma should be should be greater than 0. Okay, so if this a plus sigma is greater than 0, then this complete e to power something will become e to power minus infinity, and then this entire thing will become 0. But if this a plus sigma is negative, then this negative, and we already have a negative sign here, this will become positive, and it will become e to power infinity, and overall thing will become infinity. Okay, so this is what we call it as a convergence criteria here. Okay, this Laplace transform will converge to a finite expression only if this a plus sigma is greater than 0. Okay, so this is the convergence criteria, that a plus sigma should be greater than 0, or you can also call it as a plus real part of s should be greater than 0, because this alpha is essentially a real part of s. Okay, or you can say the real part of s should be greater than minus a. Okay, so this criteria that we use to find out the Laplace transform of e to power minus at ut, we call it as a region of convergence. Okay, it will soon be clear what it mean by region of convergence. We know what is the convergence, but what does it mean by region of convergence? Okay, so at last, this expression that you see here, this thing will become 0, and you will be left with this term, which is 1 by s plus a. Okay, so the Laplace transform this xt, which is e to power minus at ut, will be equal to 1 by s plus a, given that real part of s is greater than minus a. So this real part of s greater than minus a is what we call it as a region of convergence. Anyone has any doubt? Let me go to the next slide then. Okay. Now, just now we saw complex this number, which is sigma plus j omega. So this you can try to write with the help of this x-axis and y-axis. So sigma is, which is the real part, will be the x-axis, and the j omega, which is the imaginary part, will be y-axis. Okay. So this we call it as a s-plane. This we call it as s-plane. Now, just now we derived in the last slide that for signal e to the power minus at ut, Laplace transform will be 1 by s plus a, given that real part of s is greater than minus a. Okay, or you can say sigma is greater than minus a. Okay, now this, when you try to find the this sigma is greater than minus a on this plane, we need to check how does this thing look like on this sigma and j omega axis. Okay, so here we don't care about the omega value. Omega can be anywhere between minus infinity to infinity. We don't care about the omega. The criteria is on the sigma, and sigma has to be greater than minus a. Okay, so this is the sigma axis, and let's say this is the point where I am getting minus a. Okay, now sigma has to be greater than minus a. What it means is that if you draw this vertical line here, if you draw a vertical line here, all the point on the right side of this vertical line will correspond to sigma greater than minus a, right? Because if you pick up any point on this right side, let's say if you pick up this point or this point, for all this point, sigma will definitely be greater than minus a, because this is the point where sigma is equal to minus a. So on the right side, any point you pick up or or right side of this vertical line, on this all this point right side of this vertical line will be corresponding to this sigma greater than minus a. So this is the region, or you can say on the right side of this vertical line is the region where this Laplace transform is converging. Okay, but on the left side of this vertical line, the Laplace transform is not going to converge, because on the left side of this vertical line, sigma will be less than minus a. So if you pick up any point on the left side of this vertical line, sigma will definitely be less than minus a. Okay. So this is what we call it as a region of convergence. This is the region where your Laplace transform is going to converge to this expression. So this region of convergence is important. We will see later on how does it come into picture in the analysis of the system. Now, whenever you calculate the Laplace transform, it will be something like in this form. You will have a numerator expression, you have a denominator expression. Okay, for example, just now we calculated the Laplace transform, which was 1 by s plus a. Okay, so here the numerator is equal to 1 and denominator is equal to s plus a. Okay, so if you take the numerator and equate it equal to 0, so if you take the numerator and equate it equal to 0, you'll get since this is a function, this is some polynomial of s, when you get it to 0, you'll get some root of s. Okay, those root we call it as a 0 of the Laplace transform. And similarly, when you take the denominator and equate it to 0 and calculate the root of the s, you'll get the pole of the x of s. Okay, so this is what we call it as a pole and zeros of the Laplace transform. So in this example, where we have an expression which is equal to 1 by s plus a, here in the numerator, we don't have any polynomial of s. That means that we don't have any zeros for this Laplace transform. But on the denominator, we have a s plus a. And when you equate it to 0, you get s equal to minus a as a root of this polynomial. Okay. So this s equal to minus a is a kind of, you can say, is a pole of this Laplace transform. Okay. So this pole, when you try to locate it on this x, sigma and j omega plane, this is where the pole is located. Okay. It doesn't have any imaginary part. Since it doesn't have any imaginary part, that means the imaginary part is equal to 0. So it means that it will just be there on the sigma axis and its value is minus a. So this is the point. So this is the point where the pole is located for this particular Laplace transform, and it doesn't have any 0. Okay. So generally, whenever you see any S-plane and the pole and the 0 are noted, are given in form of S-plane, they will be given by either by this cross or this dot. So as you can see, when I have crossed here, that means that this is the point where we have one pole. And whenever you see a circle, a small circle like this, that point represents the zeros of the Laplace transform. We go to the next slide then. Yeah. So this is another example. So in this case, it is the same problem that we discussed few slides back. Only the thing is that here a is replaced by 2. So we know that e to the power minus at ut, the Laplace transform of this is 1 by s plus a, real part of s greater than minus a. Okay. So the Laplace transform of this will become this when you replace a with 2. So it will become 1 by s plus 2 and real part of s greater than minus 2. Now in this expression again, numerator doesn't have any 0, but denominator has one pole. Okay, this is 2 actually. So this is s plus 2 equal to 0. When you calculate the root, it will be equal to minus 2. Okay. So this is, you see, this is a cross sign. This is the point where we have the pole, and the region of convergence is real part of s greater than minus 2. So the green highlight that you see here, that is the region of, actually this green highlight will even go to below this line, but since I have a limitation to put the green line, I have just put it till here, but it will go all the way till infinity in this direction. and in this direction also it will go all the way till infinity, but on the left side it will have a limit till this point. It will not go beyond left of this vertical line. So this is the reason of convergence of this Laplace transform. Now there are few property of the region of convergence of the Laplace transform. First property is that ROC or region of convergence doesn't contain any pole. Okay. So the few slide back, the last slide, that the Laplace transform that we calculated, that was e to power minus 2t ut. For that we got the region of convergence is equal to something like this. Okay. And this is the Laplace transform. So if you see the pole of this Laplace transform, pole is located at -2, and the region of convergence, so this is the pole, and the region of convergence is right side of this vertical line. Okay. So this vertical line is the point where we have this pole, but the region of convergence doesn't include this vertical line. Okay. It is all the point on the right side of this vertical line. That means that this pole is not part of the ROC. It is start just after this pole, and because of that, we can say that the ROC doesn't contain any pole. Now, if xt is a finite duration signal and it is absolutely integratable, then ROC is entire as plane. Okay. So I will give you guys one example. Let's say we have a signal xt which is equal to impulse. Okay, this impulse is a finite duration signal because it is just located at t equal to 0, and it is absolutely integratable. Why? Because when you integrate the delta t, you will get equal to 1. So this is absolutely integratable and it is finite duration signal. Let's calculate the Laplace transform of this signal. So when you calculate the Laplace transform of this signal, so it is delta t into e to the power minus st dt. Now we will use this property of the Laplace, impulse, that delta t into xt is equal to x of 0 into delta t. Okay, so you can think of this e to the power minus st as a x of t multiplied by delta t, which is equal to x of 0, which means that for this e to the power minus st, we need to replace this t with 0. Okay, so this will become minus infinity to infinity delta t. Once you put this this e to the power 0, this will become 1. This term, this thing will become 1. Why? Because this is x of 0. Okay, so once you put t equal to 0, this will become e to the power 0 and it will become 1, and you will be left with this integration, and now this integration will simply be equal to 1. Now while doing this integration or calculating the Laplace transform of this delta t, I didn't take any help. Okay, I will give the, so if there is a finite duration signal and it is absolutely not absolutely integratable, there is a chance that we will not be able to find out the Laplace transform of those cases. Okay, those Laplace transform will not converge for any kind of ROC. You will see those examples also. So in this case, uh, when you are calculating the Laplace transform of this signal, we are not taking any help on this S, right? For example, for to calculate the Laplace transform of e to the power minus t ut, we took the help of real part of S, which was sigma, to make it converge, right? To converge this Laplace transform of this signal. But in this case, we didn't take any help to make this integration converge to some finite expression. That means that since we are not assuming any value for the S here, it means that for all the value of S, this Laplace transform exists. And that means that the Laplace transform exists for all the S plane. Okay? For entire point in the S plane, this Laplace transform will exist. Okay? So this is one of the example of that. Now, if the Laplace, this time domain signal is a right-sided signal, then ROC will be right of the rightmost pole. Okay, So this is just this example that we saw. This is a right-sided signal. So when you plot this signal, it is how it is going to look like. Okay, e to the power minus 2t ut. So this is a right-sided signal in the time domain. Okay, and it has one pole which is located at minus 2. And when we plotted the ROC of this, the ROC started just after the pole and it was right-sided, right side of this pole. Okay, that's what this point is saying. When the signal is the right-sided signal, the ROC will be the region. So in this case, the ROC will start from the rightmost pole. And in this case, we have only one pole. That means that it will start from this point and go till infinity. And this will happen if the signal is a right-sided signal. If the signal is a left-sided signal, that means we have, let's say, signal something like this, e to the power minus 2t u of minus t. Okay. In this case, when you plot this signal, it is how it is going to look like. It will go like this on the left side. So in this case, if you calculate the Laplace transform, the ROC will be left part of the leftmost pole, just opposite of this point. Okay, it is a right side of the rightmost pole. For the second case, it will be left side of the leftmost pole. This for this case, we will see some example also. This one. Okay. Now the last case is if what will happen if the signal is two-sided. Okay. So when the signal is two-sided, that means, let's say we have a signal which is like this, which is something like this. It is going on the both side. Okay. So if the signal is two-sided, or we can say the signal is infinite duration signal. It is going all the way from minus infinity till infinity. In that case, ROC will not be left-sided or right-sided. Okay. In that case, ROC will simply be kind of like this. Okay. So when you are going to plot this kind of ROC, this is how it is going to look like. Okay. This is your S-plane, and ROC should be greater than something but less than something. So let's say this greater than value is here, this A3, and less than value is here. So your ROC will be kind of a strip between these two vertical line. It will neither be right-sided or left-sided. So these are the four property of the ROC. So for the first case, I have shown you one example, for the second also, and for the third also. This fourth one and the fifth one, I will show some example now. So let's go to the next slide. So let's take example of the two-sided signal. Let's say we have a signal which looks like this. Okay, e to the power minus mod of t. So when you are going to plot this signal, it is going to look like this. Okay, you can also write it like this, e to the power minus t ut plus e to the power t u of minus t. Okay, so e to the power minus t ut is this part, and e to the power t minus u of minus t is this part. Okay, since there is a mod here, you can expand it like this. Okay, I hope you guys know how to expand the mod here. So after the expansion of mode, this is how it is going to look like. Now let's calculate the Laplace transform of this two cases. So first cases we have already calculated what will be the Laplace transform of first term. So we have e to the power minus t ut. The Laplace transform of this will be 1 by s plus 1, and ROC will be real part of s greater than minus 1. So this is what we got for the first one. Now let's take the second one, which is e to the power t u of minus t, and we want to calculate what will be the Laplace of this one. Okay, so let's calculate. So it will go from minus infinity to infinity, e to the power t u of minus t e to the power minus st dt. Okay, now we have a u to the power u of minus t, and because of that, instead of integrating it from minus infinity to infinity, I will integrate it from minus infinity till 0, e to the power t e to the power minus st dt. Now you can also write it like this. e to the power t 1 minus s dt. Okay, so when you integrate it, you will get e to the power t 1 minus s and divided by 1 minus s, and we need to put the limit minus infinity to, this is minus infinity to 0. Okay, so when you put limit equal to 0, this term will become 1 and you will get 1 by 1 minus s. Okay, when you put minus infinity, what will you get? You will get e to the power 1 minus s minus infinity divided by 1 minus s. And again, we want this complete integration, this complete thing to converge to some finite point, which means that we want this complete thing to be negative. Okay, negative e to the power minus infinity. That will lead yield to e to the power minus infinity. So that means that we want this 1 minus s to be positive, because minus sign is already there with minus infinity. So we want this 1 minus s to be negative. That means that 1 minus s to be less than 0. Okay, or here we are interested in the real part of s, so you can say 1 minus real part of s to be less than 0, or real part of s, oh wait, sorry, this is wrong here. Yeah, it should be opposite. So here we have already the minus sign with minus infinity, so we want it to be positive. Okay, so this will become like this. Okay, so once you calculate this, okay, this will become 0 once you have this as a reason of convergence. So Laplace transform of this signal will become 1 by 1 minus s, given that real part of s is less than 1. Okay, now we will combine this two. So we have the Laplace transform of this one, we have the Laplace transform of this one. So overall Laplace transform of this signal e power minus mod t will look like this: 1 by s plus 1 plus 1 by 1 minus s. Okay, and the ROC for this case is this much, and for ROC for this case is this. So overall ROC should be such that it is intersection of this two. Okay, so the ROC should be real part of, so overall for this signal ROC has to satisfy both cases, this cases as well as this cases. That's why we are taking the intersection. So real part of s greater than minus 1 intersection with real part of s less than 1. Okay, or you can also write it as a real part of s greater than minus 1 and less than 1. Okay, so this is how what the property that we just talked about in the last slide, that whenever the signal is both sided, ROC will look like this: greater than something and less than some number. Okay, so when you are going to plot this ROC, you can draw one line. Okay, this is minus 1, and again this side this is plus 1, and ROC will be stripped between this two vertical line. Now in this case, when you see the pole of this, okay, you can calculate the pole also. So you can also write it like this: 1 by s plus 1 minus 1 by s minus 1. So it will become s minus 1 minus s minus 1 divided by s square minus 1. Okay, and then you can also write like minus 2 divided by s square minus 1. So we have the numerator and we have the denominator. Numerator doesn't contain any s, so it means that it doesn't have any 0. But on the denominator we have a function of s, so you can calculate the pole. So in this case, pole will be s equal to plus minus 1. Okay, so we have one pole here, we have one pole here. Okay, so in this case, you see again, you see the ROC doesn't contain any pole. Instead, ROC it is just starting just after the pole and ending just before this pole. Okay, So in this case, this is how the ROC is going to look like for the both-sided signal. Now in this problem, we have also solved for, the case of the left-sided signal. This is the left-sided signal. Okay. So for this, just for this signal, if you calculate the Laplace transform, this is the Laplace transform and this is the ROC. So in this case, ROC is kind of left-sided. Okay. So for the finite duration signal, okay, so for the finite duration signal, ROC will be all entire as plane, okay, as plane. For right-sided signal, ROC will be right-sided, and for left-sided signal, ROC will also be left-sided. And for both sided signal, which is this last example that we saw, ROC will be strip between two vertical line. Strip between two line. Okay. So these are the 4 cases. Anyone has any doubt?
Sir, I have one doubt.
Yeah.
Hello.
Yeah.
Sir, in the extreme right side, you can see that three statement. I mean, inequalities. 1 minus s greater than 0, and the next step it is shown as 1 minus real part of s greater than 0.
Yeah.
So actually, I just need some clarity on that. 1 minus s greater than 0 on the next step.
Okay.
It's
Okay.
shown as.
So you can, okay, here we have e to power 1 minus s, right? You can write it as a 1 minus sigma minus j omega into minus infinity, right?
Right, sir.
And this one we can also write it as a 1 minus sigma into minus infinity, and then e to power j omega into infinity. Okay. Okay. Now if you see this expression, this is e to power j omega into infinity, and when you expand it, it will be cos omega infinity plus j sine omega infinity, right? This number. And we know
Right.
that this number can never go to infinity. It will be within like within some finite number, right?
Yeah, minus
Because
1
this is
and 1.
cos, yeah, this is cos, this is sine. That's why we are not bothered about the omega.
Okay.
We are just like we are just concerned about the real part, which is sigma. That's why I just replace this s with real part of s.
Okay. Thanks.
Anyone else has any doubt? We go to the next slide. Yeah, this is the problem just we solved, the similar problem. So here we have 2 here. So you guys can solve this problem. You'll get the similar. It is very similar to what we solved in the last slide. Now these are the few elementary Laplace transform. I've just put it as a table here. So this table, it's better to remember because this will be very useful instead of calculating the Laplace transform directly in the exam. Okay, because that will be time consuming. So some of the Laplace transform you have to memorize it, because in some cases the problem will be based on the inverse Laplace transform, not on the Laplace transform. And generally for the inverse Laplace transform, we use this kind of relationship, or you can say the pair. So if you know this is the Laplace transform, so its inverse Laplace transform will be this. Similarly for other cases also. Okay, so it's better to remember some of the Laplace transform. Okay. Now here one more thing to notice, that we have a signal u of t and we have a signal minus u of minus t, and both of them has the same Laplace transform. Okay, now the difference between these two is the ROC. Okay, so if Laplace transform is same but ROC is different, you can get back to the time domain signal. But if Laplace transform is given, but ROC is not given, in that case, its inverse Laplace transform can be this one as well as it can be this one also. If this ROC information is not given, that's why this ROC information is very critical to find out the inverse Laplace transform. Same thing you can see for this two signal also. For this two signal also, the Laplace transform is same, but ROC is different. Let me go to the next slide. I will go through the few property of the Laplace transform and then I will solve some problems. So a lot of question is generally asked based on the property of the Laplace transform. So first is the linearity. So let's say you have a signal x1t and its Laplace transform is x1s, and x2t and its Laplace transform is x2s, and its ROC is R1 and its ROC is R2. In that case, let's say you have a new signal which is like this. Okay. So the Laplace transform of this signal will simply be the linear combination of whatever you have done the linear combination in the time domain, same linear combination you do in the Laplace domain. Okay. And the new ROC will be intersection of this R1 and R2. I'll go to the next slide. Next is the time shifting. This time shifting is generally kind of important this property because a lot of question is generally asked on the based on this time shifting. So if you have any signal x of t and its ROC is R and you do the time shifting here, and so when you do the time shift here in the time Laplace domain, this Laplace will remain same. Other than that, you will be getting this multiplication e to the power minus st naught, okay? And ROC will not change here. So one example is the, let's say you have a signal ut, okay? So we know that for the unit step Laplace transform is equal to 1 by s and ROC is real part of s greater than 0. Let's say you have a new signal which is ut plus 2, okay, which is time shifted version of the ut, and we want to calculate the Laplace transform of this. So you can directly use the property, this time shifting property. So with this time shifting property, the Laplace transform will be here and multiplied by this time shifted, this e to the power minus s t naught. So t naught value is here is minus 2, so it will become e to the power 2s into 1 by s. Okay, ROC will remain same. ROC is not going to change. So in this kind of problem, if you know the property and you know some of the basic Laplace transform already, instead of going through the Laplace transform formula, you can just use this property and calculate the Laplace transform. Next is the shifting in the S domain. So if you have a signal x of s and you're shifting in the S domain, okay, so it will become s x of s minus s naught. So in the time domain, it will become like this. Okay. So here it was xt, it will become e to the power s naught t into xt. So let's say we have one example is here. So we have, let's say, signal xt e to the power minus 2t ut. Its Laplace transform is this one. Okay. Now let's say we have a new Laplace transform which is shifted version of x of s, which is this x of s minus 3. So once you do this, you will replace this s with s of minus 3, and finally you will get this. Okay, so this is the x of s minus 3. Now when you take the inverse Laplace transform of this one, you will get this signal e to the power 3t into xt. Okay, here we are getting e to the power 3t into xt based on this expression, because here s naught value is 3. Okay, here s naught is 3. So e to the power 3t into xt, and xt is this expression. Just put it here. Okay, so once you put this xt here, you'll finally get e to the power t into ut. Okay, so for e to the power t into ut, this will be the Laplace transform. Now one important thing to note is that here ROC will also shift. Okay, ROC will not remain same, it will shift, and here the shifting will depend upon what is the value of s. So if ROC is R here, in this case ROC will be R plus real part of s naught. Okay, so for example here, for the signal xt, ROC was real part of s greater than minus 2. But for the new signal, x of s minus 3, the ROC is real part of s greater than 1. Okay. In this case, it is real part of s greater than 1. So you see, instead of minus 2, you're getting here 1, which is plus 3 of the minus 2. And the plus 3 is coming because we are shifting it by 3. Next one is the time scaling. So if you have any signal and do the time scaling, this is how the Laplace transform is going to look like. And ROC will also get scaled by same factor. Okay, it will become A into R. Now let us go through one example. So this is the one of the IS problem. So let's say we have a signal Vt here, and for this signal Vt we want to calculate the Laplace transform. So one way to calculate the Laplace transform is to use this formula that x of s is equal to x of t e to the power minus st dt, and use this formula and put the x in this xt here and calculate it. Okay, but that is going to take a lot of time because you have to write the this into the some time expression, this one also in some time expression, and then put it here. Now instead of that, what you can do here is you can write Vt into some basic signal form. Okay, so for example, if you see this Vt, this is ramping up here, this is kind of ramp. Okay, this is ramping up, so let me write it RT here. Okay, but if you plot the RT, it is going to ramp up till infinity, but here ramping up is stopping here and it is becoming flat. Okay, so let's say this is my signal RT, and if you take this signal and subtract it with a new signal, which is, let's say, RT minus 1, okay, which is kind of shifted version of this RT. Okay, so it will start at t equal to 1 and it will go till infinity. When you subtract this signal with this signal, what will happen that from t equal to 0 to 1, this signal is 0 and this signal is ramping up. So after subtraction, we will get this. Okay, now at t equal to 1, this will ramp up, this is also ramping up. Okay, now if you subtract this 2 at all the point, right, for all the point you will get as a constant which is equal to 1. Okay, so if you write the equation of this straight line, it is equal to t. If you write the equation of this straight line, it is equal to t minus 1. Okay, so when you subtract this straight line with this straight line, you are going to get 1. Okay, so instead of like putting this into the Laplace formula, you can write it like this. Okay, RT minus 1. Now we know what is the Laplace transform of RT, so it is 1 by s square. What will be the Laplace transform of this one? So we will use the time shifting property, that is 1 by s square is the Laplace transform of RT, and then because of time shifting you will get e to the power s. Okay, actually I think minus s. Yeah. Now just because you know the how to write this waveform into some expression, you will be quickly able to calculate what will be the Laplace transform. Okay? So in this case, we just wrote this thing waveform into some expression, some basic expression, and then we already know what is the Laplace transform of RT and RT minus 1, and then we just put those Laplace transform and the type shifting property here. That's how we can calculate the Laplace transform of this signal. Anyone has any doubt here? Let me go to the next slide. So here the answer will be this one. Okay, actually this will be C, this will be D. So this is the correct answer. Let me go to the next slide. Okay. Now here again, this is a IS problem. So here this function is given. For this particular function, we need to find out what will be the Laplace transform. Okay. So in this case, again, it is very similar to what we saw in the last slide, but it is slightly different. Let me solve it. So again, in this case, we have a ramp, it is ramping up, but if you see the slope of this ramp, So in the last slide, the problem that we solved, the slope was 1. Okay. If you go in x-axis by 1, y-axis was also going up by 1. That means that the slope is 1. But in this case, when you go in x-axis by 0.5, y-axis is going by 1. Okay. It means that the slope here is double of what with as compared to the question that we solved in the last slide. So in this case, the slope is 2. Okay. So you can write this part as 2t. Okay, this is a straight line, okay, with 2t. So its slope is 2. So you can start with writing as ft equal to 2 into rt. Okay, rt is a ramp and its slope is 2. Okay, but if you write 2rt simply, it is again going to ramp up and going to ramp up till infinity. Okay, here we need to cut such a way that it starts to ramp down here. Okay, like this. Okay, now here this is 2 into RT. Now let's say I'm going to subtract a signal at t equal to 0.5, which is also a ramp with slope of 2. Okay. So when I take this signal and subtract this one, what I'm going to get is a ramp up and then flat. But in this problem, it is going down here. Okay. So to bring it down, I need to again subtract something. Okay. So again, I will subtract a ramp with a slope of 2. So once I take this signal and subtract again one more ramp, it is going to be like this. Okay. So what I have done is I have taken this 2RT. First time I have subtracted 2RT minus 0.5. Okay. After that I got this signal. This is minus 2RT minus 0.5. But this is not actual signal that we want. So again I have subtracted 2 into RT minus 0.5. Okay. So again minus 2 into RT minus 0.5. Now once you subtract the second this ramp, it is going to go down. Okay. But it will again continuously go down. It will not stop. We need to make it stop at t equal to 1 here. So what we need to do, we need to cancel this portion, and we know that the slope of this is minus 2. So we will again add something with slope of plus 2 here. Okay, and that should start at t equal to 1. So again 2r t minus 1. Okay, so this is the complete expression for this triangular waveform. Okay, you can also write it like this: 2rt minus 4rt minus 0.5 plus 2rt minus 1. Okay, once you get this expression, you can easily calculate the Laplace transform. So the Laplace transform will be 2 by s square minus 4 by s square into e to the power minus 0.5s plus 2 by s square e to the power minus s. Okay, this one again, if you compare with all the option, okay, so here it looks like it is given in a different form. So you can again write it like this: take the 2 to the power s square common, you will be left with 1 minus 2 into e to the power minus 0.5s plus e to the power minus s. Okay. So if you see, this is something like a square minus 2ab plus b square form. Okay, this is b square, this is 2ab, this is a square. So you can write it as a 2 by s square, a minus b whole square. So this is a, this is b, sorry, this is b square actually. So b will be minus 0.5s square. Okay. So this will be the answer. So this is wait, this one. So whenever this kind of problem is asked, it's better to break this graph into some kind of expression and then calculate it. Okay, that will make the calculation easier and faster. Anyone has any doubt? Okay, let me go to the next slide then. Okay, now next property is the time reversal. So it is kind of this time scaling property. You need to just replace a with -1. So this is when you do the time reversal in the S domain, also there will be reversal, and this will also get reversed. Okay, one basic example is ut. So for ut, Laplace transform is 1 by s, and ROC is real part of s greater than 0. But when you do the time reversal, Laplace transform is -1 by s, and ROC is real part of s less than 0. Okay, you see ROC went reversed here, and x of s became x of minus s. Now next is the differentiation in the time domain. So when you do the differentiation in the time domain, in s domain there will be multiplication by s, and this is very important property. So whenever the system will be given in the some kind of differential equation, we will be using this property to solve those kind of problem. Okay, so this is the property that is generally used when the system is given some kind of differential equation and we need to solve that problem. Next is the differentiation in S domain. So it will become multiplication by minus t in the time domain. And then next is the integration in the time domain, and it will become just opposite of this. Yet when you do the differentiation, it is multiplication by s. When you do the integration, it is division by s. Let's go to the next slide. Next is the convolution, and this is very important property. Generally question is not directly asked to do the some kind of convolution in the time domain and calculate like this kind of thing. It is generally based on some kind of the kind of problem that we'll see soon. So we know that whenever you have a system and when you give the input xt and its impulse response is st, output will be convolution of this two. Okay, but generally calculating the convolution is very much tricky. So we solve those kind of problem in the Laplace domain. Okay? We don't solve those kind of problem in the time domain. That is a bit lengthy, and it is tricky. Sometimes we people make mistake in the time domain, but in Laplace domain it becomes very easier because it is simply the multiplication of these two. Okay? So this is the convolution property. This is your time domain signal and respect to Laplace transform. When you do the convolution of these two in the Laplace domain, it will be multiplication. Next is the initial and the final value theorem. So this is the initial value theorem. So if you have the Laplace transform, just multiply it by s and put limit as tending to infinity to calculate the initial value of the any signal. Okay, but there is a catch here. You cannot use this initial value theorem for any kind of Laplace transform. Okay, so the first criteria is that the signal should follow this property that signal is 0 for t less than 0. T less than 0, it is not less than equal to, it is just less than. Okay, so signal should be equal to 0 for t less than 0, plus there should not be any high order singularity. Okay, so what does it mean by high order singularity is that when you are going to plot when you write this x of s, okay, the numerator should not have higher order as polynomial than the denominator. Okay, so for example, let's say we have this case. Okay, in this case your numerator has higher order than the denominator. Okay, and that creates the high order, that's what we call it as a high order singularity, and that creates a problem, and for this kind of cases we cannot calculate the initial value. Okay, so any of these kind of cases we will not be applying this initial value theorem. First criteria is that xt should be 0 for t less than 0, and second criteria is that x of s should not be in this form, meaning numerator should not have higher order polynomial than the denominator. Okay, last is the final value theorem. So it is similar as this, but limit as tending to 0 is here. Okay, here you will put the limit as tending to 0. So this final value theorem is applicable only when all the pole of this x of s is on the left half of s plane. Okay, so what it means is that we know that x of s will have some numerator polynomial and denominator polynomial. With the help of denominator polynomial, we can calculate what are the poles. Okay, so when you plot this pole into the s plane, all the poles should be left side of this vertical line, okay, or left side of this j omega axis. If there is any pole on the right side of this j omega axis, we should not apply this final value theorem. So these are the criteria for the initial value theorem and the final value theorem. Anyone has any doubt?
Uh, why is that? Any specific reason, like the right side?
Okay, I will give you example. So let's say I have a signal s minus 1. This is the Laplace transform. Okay, what is the inverse Laplace transform of this? So it is e to the power t into ut. Okay, now let's apply the initial value theorem here. Sorry, final value theorem here. So I have multiplied it with s, and this is the x of s, and limit as tending to 0. So when you put, it will become 0, right? But on the right hand side, when you see what it mean by when we calculate the final value theorem, what we mean is that we want to calculate time domain signal at t equal to infinity. If you see this signal is going to look like this. It is exponentially going up, and at t equal to infinity, it will become infinity. Okay. So whenever you have a pole on the right half of this plane, generally what happens that your signal in the time domain goes towards the infinity. But when you calculate the initial value, final value through this final value theorem, you get just the different answer. You won't get the correct answer in this case. You got the point here?
Yes, sir.
Okay. So again, this is the IES problem. So we have a signal f of s, g of s, and these two are the Laplace transform of the time domain signal f of t and g of t, and then their product is given as this, okay, f of s, g of s equal to h of s. Now here h of s is the Laplace transform of h of t. Then we need to find out what is the h of t out of this. Oh, actually this is again c and d. So we need to find out what is the correct expression of this h of t. Okay, so here we need to use the convolution property that we just saw, and that is that when you have the signal which is multiplication in the Laplace domain, in the time domain it will be convolution. Okay, so if h of s is equal to f of s into g of s, when you take this thing into the time domain, this will become h of t, and in the right side, here it is multiplication, here it will be in the time domain, it will be convolution. Okay, so in this case this will be the correct answer. This is wrong, and this is also wrong, and this is also wrong. So in this case this will be the correct answer, which is the convolution of the gt and ft. Go to the next slide. Yeah. Okay. Okay, this topic is very important. Generally, almost around 30 to 50% of question is based on the system, a transfer function. Okay, so let's say you have an input xt, its impulse response is ht. We know that output will be given as input convolution with h of t. When you take this complete thing into the s domain, so let's say Laplace transform of xt is as x of s, ht is h of s, then this y of t will become y of s, and that will be equal to, since in the time domain these two are the convolution, in the Laplace domain, this will become multiplication. Okay, so your y of s is equal to x of s into h of s, or you can write it as a h of s is equal to y of s divided by x of s. Okay, now this h of s that you see here, this is what we call it as a transfer function of the system. Transfer function of system. Okay, so transfer function is essentially the impulse. If you take the impulse response, calculate its Laplace transform, and you get the transfer function. Okay, so and the transfer function is given as an output Laplace transform divided by input Laplace transform. Now let me go to the next slide. Now, in the last class, we have characterized the system with the help of the impulse response. How to check whether system is causal or stable with the help of the impulse response. Okay, so for the causality, we know that if ht is something like this, 0 for t less than 0. So if your the impulse response is 0 for t less than 0, that means that our system is a causal system. Okay, now when we try to represent this into the Laplace domain, what will happen that your signal can be in the kind of two form. So on the left side it will always be 0. On the right side it can be of a finite duration signal, or it can be infinite duration signal. There are two possibility here. So if it is an infinite duration signal, okay, in that case ROC will be in the form of real part of s greater than some value, right? Because it is right sided ROC, because signal is right sided. And if it is in this form, finite duration signal, then it will be entire S plane. Okay, entire S plane. Now let's take the case when your signal is a finite duration, but it is on the left side. Okay, so in this case also it will be entire S plane, but it will be non-causal. And the last case is when it is like this. Okay, in this case also it will be non-causal, and there is a one more case, it is two-sided. Okay, then also it is non-causal. Okay, so whenever you have a ROC in the form of real part of S greater than some number and less than some number, we can directly conclude that this system is non-causal. Okay, because this kind of system correspond to this kind of impulse response, and this kind of impulse response will definitely be the non-causal. Okay, so first conclusion is that whenever ROC is in this form, your system will definitely be the non-causal. Second is about this case, whenever the ROC is in, so whenever the signal is like this, ROC will be in the form of real part of S less than some number. In that case also, system will always be non-causal. So whenever we have a system where ROC is in this form or in this form, system will definitely be a non-causal system. Okay, now in the rest of the cases where it is entire as plane, it can be or it cannot be, it depends. We need to check uh, through the time domain signal, but in this case we cannot conclude. If it is the entire S plane, it may or may not be the causal. Similarly, if the ROC is the right sided kind of ROC, it may or may not be, because for the right sided ROC can be like this also. Okay, and let me pull this. So your HT can be something like this. It is still a right-sided signal, but we have a portion for which t is less than 0 but ht is non-zero. So it means that this criteria is not satisfied. It is still the right-sided, but it is non-causal, and it can have this possibility also, which is causal. So whenever the signal is in ROC is in this form, real part of s greater than something, it may or may not be causal. Again, when ROC is in this in the form of this, which is entire S plane, it may or may not be non-causal. But if ROC is like this two form, which is greater than less than some number, or greater than some number but less than some number, these two cases, it will definitely be a non-causal system. Okay, so with the help of the ROC, we can find out whether system is causal or non-causal. Anyone has any doubt here? Let me go to the next slide. Next is the stable system. Okay, so here just pay attention here, it's very tricky thing. So for impulse response, we know that this will be the criteria for the system to be a stable system. Okay, now if you take any Laplace transform, this is how the Laplace transform looks like. Okay, in this Laplace transform, when you put s equal to sigma plus j omega and put this sigma equal to 0. Okay, so when you put sigma equal to 0, this is how it is going to look like. Okay, so what I've done, I have taken this Laplace transform, I have made real part equal to 0. This is how it is going to look like. Okay, now if you see this one will always be less than this expression. Why? Because we have mod here, we don't have mod here. Okay, so you can write it like this. Okay, now if this is converging, then this expression should also converge, because this is less than this number. Okay, so if the system is stable, it means that this is converging, this expression is converging. That means that this expression will also converge. Okay, and since this expression is converging, and we know that what is the condition here condition is that sigma is equal to 0. Okay, so that means that this integration, which is essentially a Laplace transform with sigma equal to 0, is converging. Okay, and we know that whenever the Laplace transform converges, that point is a part of ROC, correct? So it means that whenever the sigma equal to 0 is a part of ROC, the system will be stable. Everyone got my point, or should I explain it again? Okay, let me quickly explain it again. So here I arrived at this point. Okay, this two expression I have. This expression I have taken it from this one, which is the criteria for the system to be stable. And this expression, the second one, I have got from here by putting the sigma equal to 0. Okay, and let's assume that this system is stable. It means that this is going to converge. This is going to convert to some number which is less than infinity. It means that this integration is also going to converge, which is less than infinity. And since this integration is converging to some number which is less than infinity, it means that this integration is converging for sigma equal to 0. Okay, and since this integration is converging for sigma equal to 0, it means that ROC is containing this sigma equal to 0. So we have ROC, and ROC has this point. Okay, ROC should have this point, because for this point this Laplace transform is converging. So any Laplace transform where ROC is containing this line, or you can say that j omega axis, because on the j omega axis sigma is always equal to 0. So whenever you have the ROC which is containing the j omega axis, those kind of Laplace transform, those kind of system will always be stable system. Okay, so for example, this is also a stable system because this is containing the j omega axis which is sigma equal to 0. This is also containing the j omega axis which is sigma equal to 0, and this is also containing the j omega axis which is sigma equal to 0. So all these three ROC are corresponding to a system which are stable. Okay, anyone has any doubt here? Let me go to the next slide then. Now, okay, this is a very tricky question. So we have a causal LTI system with impulse response ht and input xt and output yt. They are related by this expression. Okay, in this expression we need to find out the value of the alpha such that this system is a stable system. Okay, here it is mentioned that this is a causal LTI system. Okay, so this is a, just remember that this expression, that this is a causal LTI system. Okay, now we need to find out the value of alpha such that the system is stable. Okay, now for this kind of problem we need to first find out what is the h of s. Okay, so to do that, we need to take this entire expression into the S domain. Okay, so we need to use the differentiation property of the Laplace transform. So when you do the differentiation, it is multiplication by S, and since here it is 3 time differentiation, we will be multiplying it with S cube. S cube into Y of S plus 1 plus alpha S square into Y of S plus alpha into 1 plus alpha S into Y of S alpha square y of s is equal to x of s. Now h of s is given as y of s divided by x of s. Okay, so when you calculate this, you will get 1 by s cube 1 plus alpha s square plus alpha into 1 plus alpha s plus alpha square. Okay, so this is the system transfer function. Okay, now it is mentioned that this system is a causal system, and since this is a causal system, your HT will either contain entire S-plane or it will be right-sided. There are only two possibilities, right? Either ROC will be right-sided or ROC will be entire S-plane. But in this case, we will not have the entire S-plane option because we have some poles here. We have some poles here, and ROC should not contain the pole. It means that your ROC will be in the form of like something like this. Okay, because it has to be right-sided signal. So ROC will be in the form of this, which is like something like this, real part of s greater than some number. Okay, now since it is a right-sided, it has two possibilities. It can be like this and it can be like this. Okay, so this is our rightmost pole, and in this case this is our rightmost pole. Now we know that this system will be unstable. Why? Because in this case, ROC is not containing the j omega axis. This is the j omega axis and ROC is not containing the j omega axis. In the second case, this is the j omega axis and ROC is containing the j omega axis. Okay, so all the pole has to be here or before this point. Okay, and from here only we generally conclude that whenever the system is causal, all the pole should be on the left half of the S-plane for the system to be stable. Okay, so this point you can note down. So whenever the system is causal, then for the system to be stable, all pole should be on the left half of S-plane, or all the poles should be left of this j omega axis. Okay, should be on left left half of S-plane. Okay. So all the poles should be on the left half of S-plane. Now we need to find all the pole here, and from this pole, that pole will be function of this alpha, and from there we will find the value of alpha such that all the pole is on the left half of S-plane. Okay. So for that, to find out the pole, we need to find out what is the root of this equation. Okay. So we have s cube plus s square plus alpha s square plus alpha s plus alpha square s plus alpha square equal to 0. This is the polynomial, and I want to find out what is the root of this. So you can take the s square common. Here you can take alpha into s common, and here you can take alpha square common. Okay. Now in all this expression you have s plus 1, so you can take s plus 1 common, and you'll get s square plus alpha s plus alpha square equal to 0. Okay, so this is the our expression. From there we can find out the pole. So if one pole is located at s equal to -1, that is definitely on the left half of the s-plane. Now we have some other pole also, and here we can find out the pole by finding out what is the root of this equation, s square plus alpha s plus alpha square. Okay, so this can be written as s equal to minus alpha plus minus under root p square minus 4ac, that formula that I'm using, that Sridharan formula. Sorry. Okay. By 2. Now in this expression, this term will give you the imaginary part, right? Because you see this is alpha square minus 4 alpha square. When you take out the alpha, you'll get under root -3, which is imaginary part. And only this is the real part. And generally the real part is going to decide whether it is going to fall on the left half of S-plane or the right half of S-plane. Okay. Now in this case, this is the real part, and if the real part is negative, it is going to fall on the left half of S-plane, and if the real part is positive, it is going to fall on the right half of S-plane. What is the real part? Minus alpha. And this real part, we want it to be less than 0. Okay. Or you can say we want alpha to be greater than 0. So this is the criteria for which the system will be stable. Anyone has any doubt here? So this is one of the questions that was asked in the, I think, EC gate. Let me go to the next slide then. Now this is one of the IS problems. So in this problem, we need to find out what will be the Laplace transform of the, sorry, not Laplace. So here in this case, we have a linear time system, and its step input is t square e to the power minus 2t, then the transfer function is. Okay. So when it says step input, it means that when your input is ut, your output is t square e to the power minus 2t. Okay. So when your input is ut, output is t square minus e to the power minus 2t. Okay. Now h of s is given as, this is the transfer function, y of s divided by x of s. Okay, we know what is the x of t, we know what is the y of t. We can calculate what is the Laplace transform of this x of t, what is the Laplace transform of y of t, and just divide these two to get the transfer function. Okay, so the Laplace transform of ut is very simple. So ut is 1 by s, and for this one we need to use some of the property to calculate the Laplace. So first is, so this is actually there will be ut here. So t square e to the power minus 2t ut. For this one we need to find out what is the Laplace. So first step is, we know that what is the Laplace transform of this signal. So this signal, okay, this one, this is the Laplace transform of this signal. Now whenever you do the differentiation in S domain, on the time domain you will have to do the multiplication by minus t. Okay. So when you do the differentiation in S domain, in the time domain you will multiply it with minus t. Okay, so here it will become, okay, something like this. This minus and minus you can cancel out. Now again, but here we have a t square, so again we will do the differentiation here. Okay, let's do the differentiation again. So when you do the differentiation again, this will become d by ds of s plus 2 whole square, and on the left side it will become minus t square e to the power minus 2t ut. Okay, so here we are using this property that multiplication in time domain by t is differentiation in s domain. If you don't know this property, you will not be able to solve this problem. That's why here the property is important to solve this problem. So here when you solve this, you'll get this. This and this will cancel out each other. So this is the Laplace transform of this one, which is 2 by s plus 2 cube. Okay. Now so this is our y of s. We know what is x of s, which is 1 by s. So when you put it here, you'll get this 2s divided by s plus 2 whole cube. Okay. I think there is a one problem here. Either this is 1 here or this is 2 here. Okay, I think this is 1 here. I will cross check again, but yeah, this is the answer then in that case. So here we have just divided ys with x of s. It will be give us 2s divided by s plus 1 cube if it is e to the power minus t here. So here we have used the two concepts. First is the property, which is differentiation in time domain. Second thing we have used is this one, that h of s is equal to y of s divided by x of s. We go to the next slide. Okay. Next is the inverse Laplace transform. So for the signaling system, we are not going to use the inverse Laplace formula, which is given by this we will see in some of the mathematics book, that this is what you can use to calculate the inverse Laplace transform, but generally calculating the inverse Laplace transform through this formula is very lengthy. Okay, so what we do is, we already know what is the Laplace transform pair. For example, ut Laplace transform is 1 by s and so on. So we take the help of this pair to calculate the inverse Laplace transform. Okay, so we generally use the partial fraction method as well as already known Laplace transform pair to calculate the inverse Laplace transform. Okay, so for example, let's say we have been given a Laplace transform and ROC is this, and we were asked to find out what will be the inverse Laplace transform. Okay, so here we have x of s is equal to 1 by s plus 1, s plus 2. Okay, and ROC is real part of s greater than minus 1. So this is how the ROC looks like. And since ROC is in this form, the inverse Laplace transform of this signal will be right sided, okay, not the left sided. Now let's first step is to take the partial fraction of this. So once you take the partial fraction, you'll reach to this point. Okay, now here you have 1 by s plus 1. Now 1 by s plus 1 has two possibility in inverse Laplace transform. First possibility is the right-sided. Second possibility is the left-sided. Okay. For the right-sided, this will be the ROC. For the left-sided, this will be the ROC. But we know that our signal is the right-sided. Okay. So we will discard this choice. We will pick up this choice. Okay. So the inverse Laplace transform of this one will be e to the power minus t ut, and for this expression will be e to the power minus 2t into ut. Okay. So this is how we can calculate the inverse Laplace transform. So here we have already used the already known inverse this Laplace transform pair. So these two are the pair and these two are also the pair, and we have used this non Laplace transform pair to calculate the inverse Laplace transform. If you don't know that these two are the pair, then it will be difficult to calculate the inverse Laplace transform. Anyone has any doubt? Yeah, let me go to the next slide then. Now, in this example, it is a same Laplace transform, but I have changed the ROC. Okay, so we will check how does it this ROC change will change the inverse Laplace transform. So in this case, this is the ROC. These two are the pole, -1 and -2, right? This pole and this pole, and our ROC is stripped between these two poles. Now again the partial fraction expression will be same, but when you take the inverse Laplace transform, you have to be careful because here the ROC is different. So for the first case, which is 1 by s plus 1, okay, your pole is here and ROC is kind of left of this pole. Okay, so for this particular expression, which is 1 by s plus 1, we should apply the left-sided signal, because with respect to this pole, okay, for this expression, pole is at -1, okay, which is here, this one. So for this pole, the ROC is on the left side, and because of that, we should use the left-sided signal for this expression, and that will be this one. And for this one, this is the pole and ROC is on the right side of this, so we will use the right-sided expression. In the last slide, for both of the pole, if you see the last slide, for both of the pole, ROC is on the right side, and that's why we have chosen the right-sided signal for both of them. In this case, based on where the pole is located with respect to ROC, you should use the either left or right. So if you take the pole, ROC is on the right side of the pole, you should use the right-sided signal. And if you take the pole and ROC is on the left side, you should choose the left-sided signal. Now, if you see this complete expression, this is both-sided signal. So by both-sided, what I mean is that if you plot it, it will look like this. Okay, so it means that it is there for -infinity to infinity. Since this is a both-sided signal, its ROC will be stripped between two vertical lines. Okay, so that's all. That is another way to verify that. When you take the inverse Laplace transform, if this is both-sided, ROC will be stripped between two vertical lines. Okay, and you see this is both-sided. This will be right side, and this will be left-sided. Anyone has any doubt here? Okay. Now this is the last case. Again, the same Laplace, ROC has changed. Now in this case, ROC is like this. Now in this case, for both of the pole, ROC is on the left side. Okay, for both of the pole, ROC is on the left side, and because of that, we will choose the inverse Laplace transform such that for both of the expression, the time domain signal is left-sided. So this is also left-sided. This is also left-sided signal. Okay. Go to the next slide. Now we have a question here. So we have been given a system which is in differential equation format, and we need to find out what will be the impulse response of this kind of this kind of system. Okay, so here this so one way to find out the impulse response is to solve this in time domain, but we are not going to use it. That is going to be very lengthy. We are going to use the Laplace. So let's take this equation and calculate the Laplace. So on the left side here, it's 2 time differentiation. So it will be s square into y of s plus a plus b. And here it is 1 time differentiation. So it will be s into y of s. And then plus ab equal to x of s. Okay. Now we need to find the impulse response, which is h of t, and h of t is Laplace transform, inverse Laplace transform of h of s. Okay. Now y of s by x of s will give us the h of s. Okay, and that will be given as okay. Actually, there is something missing. I think I forgot to type y here. There will be y here also. So this will be y of s here. When you take this, it will become s square by a plus b s plus ab, and you can also write it s plus a s plus b. Okay, so now we have got the h of s. Now we can calculate what will be the h of t. Okay, now to calculate the h of t, we will calculate its inverse Laplace transform. Okay, now when you calculate the inverse Laplace transform, here you will get, you need to do the partial fraction, and you'll get something like this kind of form: 1 by s plus a, 1 by s plus b, something like this. Okay, and when you take the inverse Laplace transform, you'll get something like e to the power minus at into ut, and for this one you'll get something like e to the power minus bt into ut. Okay, and there will be summation sign or subtraction sign between these two. Okay, now if you see this option, this option will go away because this is not in the form of this. Okay, this option will also go away. This is multiplication of these two. Here we need either subtraction or addition. Now if you see this expression, this will also go away because here we have e to the power minus bt and here we have e to the power at, but we need e to the power minus at. Now we are left with this expression which has this two form. So here we don't need to find out the exact expression here. Here it is just asking the realization. It can be realized using which of the impulse response. Okay, here it is not asking the exact impulse response. So this will be the correct answer. Okay, now one question one can ask here is that here ROC is not given. Here we have been given h of s, but ROC is not given. Then how are we calculating the inverse Laplace transform of this? So here one thing to remember is that whenever you have the Laplace transform and ROC is not given, you always assume that the signal is a causal signal or system is a causal system. Okay, this you have to assume only when ROC is not given. If the ROC is given, don't assume anything. But if ROC is not given, always assume that system is causal or signal is causal. And whenever you assume that system is causal or signal is causal, what happens that ROC becomes in the form of this. Okay, real part of s greater than sigma, and because of that in time domain signal it becomes the right-sided signal. Okay, and that's why we have taken the right-sided inverse Laplace transform, not the left-sided. So this thing you have to remember in some of the problem. If ROC is not given, assume that it is a causal and then solve the problem. Any doubt?
No doubt on this slide, sir. In the previous slide, I think we have missed something.
Or this problem you are asking?
I haven't seen it. I thought something we have missed. Okay. It's a question, right?
Yeah, it's just a question. Actually, it's kind of homework generally. So yeah, you guys can solve this problem. Yeah, it's just
Okay.
an exercise. Yeah.
Okay.
Okay. Now, before going to this problem, we will solve this problem. This is a very good problem. So if impulse response of this continuous time system is h of t, then what will be the step response of the system? Okay. So we have a system, its impulse input is impulse, so its output will be impulse response h of t. Now what we need to find out is that when input is u of t, then what will be the output? Okay. So in this case, output we can write it as a convolution of input, which is u of t with h of t. Okay. This we can also write it as a minus infinity to infinity u of tau h of t minus tau d tau. Okay, this is one way to write it. Now if you see this this expression here, the option is in this form, so you can write it like this also: minus infinity to infinity h of tau u of t minus tau d tau. Okay, these two are interchangeable, that we have seen in the convolution property in the first class. So h of tau u of t minus tau d tau. Okay. Now here be careful that the tau is variable, not t. Okay, here the tau is variable and this is ut minus tau. Okay, so if you plot this ut minus tau as a variable in this, so let's say I'm just plotting first just u tau. So this is how the u tau is going to look like. Okay, start from 0, go till infinity, value is 1. Okay, now let's say I want to plot what is the u tau plus t. Okay, in this case we are shifting this by t amount. Okay, and we don't know what is the sign of t, so I will just assume that it is, let's say, something like this. Okay, this is the point t, and this is ut plus tau, going, this axis is tau. Now let me plot the ut minus tau. Okay, so when you do the replace this tau with minus tau here, you are essentially doing the time reversal, and because of that this complete thing is going to get flipped like this, and this will become t, and this is going to minus infinity, something like this. Okay, and actually this is minus t here. Yeah, because when you do t here, it will shift left by minus t. So when you flip it, this minus t on the right side will become plus t, and it is going from minus infinity to t. Okay, this is ut minus tau. So from t equal to t, sorry, tau equal to t to infinity, this thing is 0. Okay, that means that when you do this integration, you can remove the t tau equal to t to tau equal to infinity limit, right? You can just integrate it from minus infinity to t. Okay, so you can integrate it from minus infinity to t h of tau d tau. Okay, so this will be the your what we call this unit step response. Okay, this is the unit step response. So this is universal derivation kind of, because you can use it in anywhere. Whenever you have the impulse response, you want to find out the step response, just integrate the impulse response, and that will be the correct answer. Okay, so this three options are wrong, and this will be the correct one. So again, this problem was asked one of the ES problem. Previous year ES, I think I have not written it which one, but yeah, this one is very good problem. And this one you can solve it through this expression also. We try to solve it with the bottom one. You can solve it with the help of top one also. So in the top one, what you can do is, this is u tau, simply u tau. So that means that you can write it like this, minus infinity, sorry, minus infinity, 0 to infinity just. So you can write it from 0 to infinity, h of t minus tau, t tau, okay? And here we have put 0 to infinity because we have u tau, and u tau means u tau will be equal to 1 for tau equal to 0 to infinity, and u tau will be 0 for minus infinity to 0. Okay, that's why we are just integrating it from 0 to infinity. Now this is ht minus tau d tau. You can, let's assume that t minus tau is equal to u, so d tau will be equal to minus du. Okay, so you can write now as a, so when limit is 0, u will be equal to t, and when limit is infinity, it will be minus infinity here, h of u du, and there is a minus sign outside because this is minus du. Okay, now let's remove the minus sign and change the limit, so it will become minus infinity to t h of u du, which is same as this one. So you can go in anywhere, you can go through this one also, you can go through this one also, both will give you the same result. Anyone has any doubt? Let me go to the next slide then. This will be the last problem for today's class. So in this case, we have a continuous time LTI system. A step input, response to the step input is this. So that means that you have a system, and when you give the input as a step, unit step, your output is going to be 1 by 2, 1 minus e to the power minus 2t ut. Okay, and for this case we need to find out what is the impulse response. Okay, you cannot find out the impulse response directly in the time domain, you need to take the help of the Laplace. Okay, so we need to, ht is the inverse Laplace transform of h of s, so we will first find out what is h of s. So h of s will be equal to y of s divided by x of s, where y is the output Laplace transform of this one and x of s is the input Laplace transform. So this is, we know this will be Laplace transform of ut will be 1 by s. We need to find out the Laplace transform of this one. So you can also write it 1 by 2 into ut minus 1 by 2 e to the power minus 2t ut. Okay. For this one, it will become 1 by 2s minus 1 by 2 s plus 2. Okay. Or you can write 1 by 2, 1 by s minus 1 by s plus 2. So it will become s plus 2 minus s divided by s plus 2 into s into 2. Okay. So this will be the output. Okay. Now let's calculate. So I'll put the output Laplace and then put the input Laplace. This will cancel out. You'll get 1 by s plus 2. Okay. For 1 by s plus 2, inverse Laplace transform will be e to the power minus 2t into ut. Okay. Here ut is not written by mistake, so this will be the correct answer. So whenever the question is asked based on the system where some input is given, some output you need to calculate, or input and output is given, you need to calculate the transfer function, all this kind of problem, you need to use the Laplace transform. That will make this calculation pretty easier.
Sir, I have a doubt, sir.
Yeah.
Sir, actually, in the question it's shown as we got the step input response. So if we differentiate the step input, then we will get in impulse response directly or not. I just have a doubt. We
When
heard,
you differentiate the, yeah,
I
you will
think
get
we
that.
get
Yeah.
we get the same answer. I guess.
Yes, got it. Yeah. So whenever the step input is given, you can differentiate it and you will get the, yeah, correct.
Okay. Thank you.
Yeah. So yeah, when you're differentiating it, right, you be careful that this expression and this expression, these two are multiplication of each other. Like you need to differentiate it like first function multiplied by. So what I mean is that when you differentiate it, let's say two function, okay, you do it like this, right? Xt d by dt of yt plus yt d by dt of xt, right? So you need to differentiate it like that. First function, second function, and then differentiate. Okay. Don't assume that this ut will be a constant. This ut will also be a function. So people make mistake here that they assume that this ut is a constant. So with that also you'll get the same answer. Any other doubt?
No doubt, no doubt.
Okay. Okay. Then if no one is doubt, then I will stop the class here.